Next, let's prove a theorem about intersection of two subgroups. Let's say H and K be subgroups of G. G is, of course, is a group. Then H cap K is a subgroup of G. Okay, so to prove this theorem, we need to check this intersection satisfies the subgroup criteria. So, but in order to apply that criterion, we need to check whether this, we need to check that this is not empty. Okay, so since the identity element is an element of both H and K, as we have seen before. So identity element is always an element of any subgroup. Okay, so since this identity element belongs to both H and K, therefore E belongs to H cap K. Therefore, H cap K is not empty. Okay, so that's one thing. Now, we check the subgroup criterion. Okay, so let A, B be elements of H cap K. Then this means A and B belong to H. Therefore, A, B belong to H. And A inverse is also an element of H. And at the same time, since it's intersection, A, B also belong to K. Therefore, A, B belong to K. And A inverse belongs to K. Okay, this is because H and K are supposed to be assumed to be subgroups. So therefore, they do satisfy these criteria. Okay, then this means so AB belongs to both H and K. Therefore, AB belongs to H cap K. And also, A inverse belongs to both H and K. So that means A inverse belongs to H cap K. Therefore, but this AB are just any elements of H cap K. Therefore, by the subgroup criteria, H cap K is a subgroup of G. And we are done. By the way, even if H and K are subgroups of G, H cap G, so H cap K, this union is usually not always a subgroup of G, unless you're lucky. This cannot be a subgroup of G in general. The next theorem shows the necessary condition for this union to be a subgroup. Okay, and suppose H and K are subgroups of G. Okay, and suppose H cap K is a subgroup of G. Okay, then either H is a subset of K or K is a subset of H. Okay, let's prove this theorem. Now we need to prove either this or this, but without losing generality, we may assume this is not the case. Okay, if this is the case, then that's fine. We just swap the roles of K and H and do the same thing. So let's say without losing generality, assume H is not a subset of K. Okay, then there exists some element of H such that H does not belong to K. Okay, so since H is not a subset of K, so there is some parts of H which is not a part of K. So we pick one element from that. So let's say it's H. Okay, and now since this is by assumption this is not the case, we need to prove this is the case. Okay, so we need to prove K is a subset of H. So to prove that, let A be any element in K. Okay, what we want to prove is from here we need to deduce that A is an element of H. Okay, so this is our goal. So first let's assume this. Then what happens? Okay, H is an element of H. Lowercase h is an element of uppercase H. So A and H are both elements of H cup K. Right? This is a union. And by assumption, H cup K is a subgroup. Okay, subgroup of G. Okay, that means therefore AH, their product, is an element of H cup K because it's a subgroup, so it should be closed under multiplication. So therefore A times H is an element of H cup K. So this means AH belongs to either H or AH belongs to K, or both, right? But suppose, suppose this is true. AH belongs to K, then what happens? And we are assuming A is an element of K and K is a subgroup. Therefore, A inverse is also an element of K. Remember the subgroup criterion. So if A is an element of the subgroup, then A inverse is also an element of the subgroup. Then, if that's the case, if we multiply AH by A inverse from the left, then A inverse times AH is equal to A inverse AH by associativity, which is identity element, and identity element times H is just H. But K is a subgroup, so this product belongs to K. But this contradicts our assumption that K, this element H does not belong to K, right? Which is a contradiction. So what was wrong was this assumption. So suppose AH is an element of K. So therefore, because of this assumption, we reached this contradiction. Therefore, AH does not belong to K. So that means, so this is rejected. Therefore, AH must be an element of H. Okay, but H inverse is an element of H because H, this lowercase h belongs to this uppercase H, which is a subgroup. Therefore, this lowercase inverse is also an element of this uppercase H. So if we multiply AH from the right, then by a H inverse, then this is A. And since this is an element of H and this is an element of H, therefore their product is an element of H. Therefore A is an element of H. So after all, if we assume A belongs to K, then A is an element of H, which means K is a subset of H. And we are done. Okay, now consider this group. This is called dihedral group of order 8. It's named D4 for short. Dihedral group. Of actually, not order 4, it's order 8 of. So it's written 4 here, but its order is 8. So here, please try to find the subgroups from this group. So there are 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. And I will tell you the answer. Subgroups are these. I mean proper subgroups. Okay, E, B, and E, D, and E, G, and E, F, and E, H. And so these are subgroups with 2 elements of order 2. So another subgroup is E, A, B, C. So subgroup of order 4, E, B, D, G, and E, B, F, H. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 subgroups. And of course, there are trivial groups, subgroups. So that is only one element, and there is D for itself. D for itself. That is E, A, B, C, D, F, G, H. Okay, so these are all the subgroups of this D4. Now, the first 6, this one, this one, this one, this one, this one, this one, they are cyclic groups. And the last 2, this one and this one, are Klein 4 groups. So Klein 4 groups. And these are cyclic. And you should check that. Let's see, let's take this one as an example. So E and B, so let's try to construct the Cayley table for this. E, B, B, and B times B is E. So indeed, this is closed under multiplication. And of course, B squared is E, so it is cyclic. And ED also. Let's try that. And ED, D, and D times D, D times D is E. So it is closed under multiplication, and so on. You should try those for all these groups. And for the client for groups, we have seen the Cayley table for the client for groups before. So this is the Cayley table of the client for group. So here we have E, B, D, G. So replace these A, B, C with E, B, D, G. So B, D, G, and B, D, G, and replace all these. And so B times B is B times B is E. So this is okay, and okay, let's see, B, D, G, okay, B, D, G, and B times D is G. So C is replaced with G, so that's okay, and D times B should be also G. Let's check. B times D is G, yes. D times D. D times B is also G. So that's okay, and so on. So if you check that, this pattern of this Cayley table is identical to this table of the Klein for group. And the same applies to this one also. EBFH. So replace this with BFH, BFH, then you will see this fits the pattern of the Klein for group.